I'm here to talk about series LC circuits. We're gonna review about the impedance equivalence of LNC circuits. Next, we're gonna study the behavior of LC circuits with DC excitation. Then, the behavior of LC circuits with AC excitation. Lastly, we're gonna have problems. We're gonna analyze the circuit of LNC circuits. Impedance equivalence of LNC circuits. So we remember that the impedance of an inductor is J times the inductive reactance, and the impedance of the capacitor is negative J times the capacitive reactance. So when you connect these two in series, we get the impedance of an LC circuit is equal to J times the quantity of inductive reactance minus capacitive reactance. This is the complex impedance. So, however, the magnitude of the impedance of an LC circuit is equal to the absolute value of the quantity of XL minus XC, or the inductive reactance minus the capacitive reactance. Okay guys, behavior of LC circuits with DC excitation. So what happens when you connect an inductor and a capacitor to a DC supply? First, we'll study each component separately. When an inductor is connected with a battery in a circuit, current will flow in the circuit. But the rate of rise is not instantaneous. It does reach the maximum value, but it takes some time. And in the process, energy is stored in its magnetic field. Next, if a capacitor is connected with a battery in a circuit, the capacitor will allow the flow of current in the circuit and stores energy in its electric field. When the capacitor voltage equals the battery voltage, flow of current stops as there is no potential difference in the circuit. So when both elements are combined in a circuit with their DC supply, each one stores energy in their respective fields. The inductor stores energy in its magnetic field, while the capacitor stores energy in its electric field. When the current in the circuit reaches a maximum value, the capacitor has charge with the battery voltage. Since there is no potential difference now, the current should stop flowing, and the line in the graph should drop to zero. But the presence of an inductor doesn't allow the sudden change of current in the circuit. It acts as a voltage source now, driving the current in the same direction till the value drops to zero. In the process, energy in the conductor is transferred to the capacitor. Therefore, the capacitor charges 2 times the supply voltage. Done. So guys, behavior of LC circuits with AC excitations. So, since all our elements in this circuit are now connected in series, every point in this circuit has the exact same amount of current passing through it. With each component connected in series instead of in parallel, the inductor and the capacitor combination acts like a short circuit instead of like an open circuit. So, this inductor-capacitor series combination could be replaced with an open circuit, short circuit, and the AC voltage doesn't even know the difference, because if you it would look like this, because they have the exact same amount of current passing through it. So, however, this is only true if the frequency of the voltage source is exactly equal to the resonating frequency. The closer the frequency of the voltage is to the resonating frequency, the more the inductor-capacitor series combination will look like a short circuit. And the larger the current amplitude capacitor series combination will look like a short circuit will be. The opposite is the case if it is connected in parallel. Thank you.
The resonating frequency of the inductor-capacitor combination is still exactly the same as before. With the components connected in series instead of in parallel, the inductor-capacitor combination acts like a short circuit instead of like an open circuit. This inductor and capacitor in series could be replaced with a short circuit, and the AC voltage source wouldn't know the difference, because the exact same amount of current would be flowing through the AC voltage source as before. However, this is only true if the frequency of the voltage source is exactly equal to the resonating frequency. The closer the frequency of the voltage source is to the resonating frequency, the more the inductor-capacitor series combination will look like a short circuit, and the larger the amplitude of the current will be.
So guys, let's try some sample problems. Okay, a series circuit consisting of a 0.08 Henry inductor and a 150 microfarad capacitor is connected across a 100 volt 60 Hz source. Determine the current drawn. So this problem tells us to find the current, where to start off, I is equal to V over Z, where Z is equal to the absolute value of inductive reactance minus capacitive reactance. To find the inductive reactance, we have the formula 2 pi FL, and the capacitive reactance is equal to 1 over 2 pi FC. So let's substitute the values of each. So 2 pi, the frequency, which is equal to 60 Hz, times the inductance, which is equal to 0.08 Henries. So let's figure out what the value 2 times 60 Hz times 0.8 Henries is equal to 30.16, and this other one is 1 over 2 pi 60 Hz times 150 times 10 to the negative 6, which equals to 17.68. Okay, the impedance is equal to 12.48. So let's go back to the first formula. We have I is equal to the voltage, which is 100, divided by the impedance, which is equal to 12.48, which equals to 8.01 amperes. That's all. So guys, let's start another problem here. So, 5 microfarad capacitor is connected in series with a variable inductor to a 20 volt 796 cycle source. For what value of inductance will the current be 2 ampere lagging? So, if it's lagging, the inductive reactance will be greater than the capacitive reactance. So, the formula will be like this. Z is equal to XL minus XC. So to get the impedance, we have the formula Z is equal to the total voltage over current, which is 20 volts over 2 amperes, which is equal to 10 ohms. So first, we have to get the capacitive reactance, which is equal to XC is equal to 1 over 2 pi FC. So let's substitute the values. 1 over 2 pi 796 hertz times 5 times 10 to the negative 6 farad. So to figure out the value, we have to get our calculator. So here we go. So the value is equal to 40 ohms. So Z is equal to XL minus XC. Substitute 10 ohms is equal to XL minus 40. So we get XL is equal to 50 ohms. Then to get the inductance, we have the formula L is equal to XL over 2 pi F. Then we substitute the values. 50 ohms over 2 pi 796 hertz, which equals to 6 times 10 to the negative 3 henries, or 6 millihenries. That's all.